I think you can see this. So first of all, level 3. So we want to find the sum of all real x such that this equation is true. 4x squared plus 15x plus 17 divided by x squared plus 4x plus 12 is equal to 5x squared plus 16x plus 18 divided by 2x squared plus 5x plus 13. And so one of the first things we can notice is the fact that these two are, we just need to add x squared plus x plus 1 to here to get to here. And at the same time, this just needs to add x squared plus x plus 1. And so that means that if we let this be f of x, this be g of x, and x squared plus x plus 1 be h of x, then this just simplifies to f of x. Then this simplifies to f of x divided by g of x is equal to, excuse me for a second. Sorry about that. So f of x over g of x is equal to f of x plus h of x divided by g of x plus h of x. And so we can cross multiply here. And so that just gives f of x, g of x plus f of x, h of x equals f of x, g of x plus g of x, h of x. And so these two are equal, so we can cancel them out. So f of x, h of x is equal to g of x, h of x. And so now what we really want to do is be able to divide out these h of x. And so h of x is equal to x squared plus x plus 1. And we can simplify this by completing the square to get this to be equal to just x plus 1/2 squared plus 1. Sorry, not plus 1, plus 3/4. And so this is always greater than 0. And in fact, it's always at least 1/2, sorry, 3/4. And so that means that we can divide this out. And so what we're left with is f of x equals g of x, or just the fact that using these up here, 4x squared plus 15x plus 17 is equal to x squared plus 4x plus 12. And so we can move everything to one side to get that 3x squared plus 11x plus 5 is equal to 0. And so now we want to find the sum of all real x. So either there are no real solutions x, no real solution x, or the sum is equal to negative 11 over 3. And this is just because of YEA does. And so what we need to do is check whether or not this has real roots. And so the easiest way to do this is by finding the discriminants. And this is equal to b squared minus 4ac, or 11 squared minus 4 times 3 times 5. And so this is 61. And since this is greater than 0, we have that the sum is negative 11 over 3. And so the sum of all real roots is just negative 11 over 3. And so does anyone have any questions? Okay, if not, let's move on to this one. So next up, a word is defined using a finite string of letters. And so it's a palindrome if it reads the same backwards and forwards. Oops. Okay. So now we let a sequence of words like this be defined as in this manner. So W0 is A, W1 is B, and for all n at least 2, Wn is simply writing the word Wn minus 2 followed by W of n minus 1. So for example, we can see that W2 is BA, W3 is BAB, and so on. Okay. So now we want to prove that for any n at least 1, the word that you get, sorry, this is AB. And so that this is BAB. Okay, now that's right. The word formed by writing W1 through Wn in succession is a palindrome. So just in order to simplify this, we can define R of A1, A2, all the way to AN to be just AN, AN minus 1, so on to A1, where AI are letters. Okay, and so now if you want, you can induct, and so we look at the reverse of word 1 to word K. And so if we want, we can induct to show that this is just simply equal to the reverse of WK all the way to, reverse of WK, reverse of WK minus 1, all the way to reverse of W1 in this order. So we can see this through inducting based off of the definition of R and just simply because of the recursive definition of W. And so now we already know that W1 is B, and then W1, W2 is BAB, and W1, W2, W3 is BAB, BAB. And so we can confirm that all three of these are palindromes. So now we can define n is at least 3. And so we now assume R of W1, W2, all the way to WK is equal to, W1, W2, all the way to WK for all K between 1 and n. And so this is really what we want to prove. And so this is basically the base case for the induction, and this is now the inductive step. And so now we look at R of W1, W2, all the way to W of n plus 1. So by using this, we can see that this is simply just R of Wn plus 1 times R of, times, whatever. It's R of W of n plus 1, then iterated by R of the reverse of W1, W2, all the way to Wn. Because we can effectively treat this whole thing as one word, and then it would fall under here. Of course, we can also combine it with this, and that just gets this. Because we can basically piece it apart into this, and then this portion can combine into this. And so this is as we already know, just so we can split W of n plus 1 into W of n minus 1, W of n, and we can split this into W1, W2, all the way to Wn minus 2, Wn minus 1, Wn. And so, once again, this is just R of Wn minus 1, Wn. And this here, we can just take this out and turn it to R W1, W2, all the way to Wn minus 2. And so this, we can combine them to form W of n plus 1. And so now, by using this and our inductive assumptions again, we can simplify this into R of W1, W2, Wn, and then times W of n plus 1. And so finally, we know that this works when k is n. So we can see that this is equal to W1, W2, all the way to Wn plus 1. So we've shown that this is a true statement. And so the inductive set is complete. And so we've shown that W1, the word formed by writing W1, W2, and so on, up to Wn in succession is a palindrome. And so does anyone have any questions? Okay, well, if not, then I guess thank you for coming. And so a couple of quick announcements. So next Friday, the guest speaker will be Catherine Lee, and Zachary Chung will continue going over his weekly physics challenge problem. And so once again, thank you for coming and have a nice week. Bye.
Sayonara.